Hello, everyone. This is a short discussion for Tuesday, March 24th. So, Section 8.2 is due today. Please email that to me as soon as you can. Look for solutions posted on the website, course website. And 8.3 is due next time. We have quite a bit of discussion on Section 8.3 in the discussion for last Thursday. And then 8.4, I'll go over some items for that now, although we've done a lot of that already. And then there's one problem in Section 8.4 that I want to go over. And then this is the end of the material for the second exam. So the second exam will be on Thursday, April 2nd. Okay? And that's going to be a take-home exam. All right. So comments on assignment. For section 8.4. Okay. Number 8. Number 8 is pretty self-explanatory. It just gives you a homomorphism and asks, gives you a function. Verify that's a homomorphism and find its kernel. So, that's just a basic sort of problem for this section. Number 18. This is very similar to an example, to the example for Q8 done in the lecture for section 8.4. So, we found all homomorphic images for Q8. All right, that is all H such that there is surjective homomorphism F from Q8 to H. So we found all possible groups H, such that there's surjective homomorphism. In other words, we found all quotients of Q8. All right, so by first isomorphism theorem, H is all possible Q8 mod N, or mod K for kernel, right? It's all Q8 mod K. So this one is, so we did that in the lecture notes for section 8.4. And number 18 is do the same thing for D8. So not found, but find all homomorphic images for D8. That is all H, so there's a surjective homomorphism from D8 to H. Right? In other words, all quotients, D8 mod K. But one caveat to this, right? In Q8, all subgroups are normal. Not so in D8. Not all subgroups are normal. There's a few, but not all of them. Okay? right? So, yeah. So, just like the example there. All right, so that's 18. Number 22. So number 22, it's a substantial problem, but it's split into three parts. And each part, is really self-explanatory again. But what you get in the end there is really something substantial and important for abelian groups, and we will touch on this later. Actually, number 22. So in section 9.2, I believe it is, we'll actually touch on that idea that's presented in number 22. So it's a substantial result, but it's split into three parts, so it's not it's not that bad. And then number 26 is like number 25, which is in the lecture notes for section 8.4. Okay, all right. So just some comments there on section 8.4. Now, I would like to, on the assignment for section 8.4, and then the last thing in section 8.4 I want to talk about is number 33. So 8.4 number 33 is often called the fourth isomorphism theorem. Right? Or it's called the correspondence theorem. Okay, so it's either called this or that in the context you got going here. And it goes as follows. Let f from G to H be a surjective homomorphism with kernel of f equal to k, right? That is, k is just some normal subgroup of G. Right, I mean, by the first isomorphism theorem, if you have a surjective homomorphism with kernel k, then H is just isomorphic to G mod k. Right, so, you can set it up either way. Say K is a normal subgroup of G, or F from G to H is a surjective homomorphism. There's no difference really. Exactly is their wording here. That's 32. 33. Yeah, that's a. Well, anyway, they don't need to say homomorphism here. I'm not exactly sure why they did. Anyway, show that. So let X be equal to the set of all A, which are subgroups of G, such that K is a subgroup of A is a subgroup of G. And let Y equal the set of all B, such that B is a subgroup of G mod K. Okay. So X, the set of all subgroups of G that are that contain K itself, and Y, the set of all subgroups of G mod K. Show there's a bijection from X to Y. Okay. Show there's a bijection from X to Y. All right. Well, first of all, so what is the bijection? Well, we're going to define a function from X to Y. So define the function. Okay, since K is a normal subgroup of G and K is a subgroup of A, right? It must be that K is a subgroup of G that K is a subgroup of A is a subgroup of G. Since K is a normal subgroup of G and K is a subgroup of A is a subgroup of G, it must be that K is a normal subgroup of A. Why? Because, for every element A, little a in A, the element little a in A is also an element in G. So Ka has to be equal to AK because this relationship is satisfied for every element of G, which, A is just some sub thing of the elements of G. So it's just by definition, really. So the function A goes to A mod K is a function from X to Y. Not a homomorphism, just a function. It's not a homomorphism because these aren't even groups, they're just sets. From X to Y. Alright, so now we want to show function is surjective. Okay, so this correspondence A to A mod K, it's a function from X to Y, and I want to show it's surjective. Right, so Y is the set of all B that are subgroups of G mod K. Right, so a subgroup of G mod K, it's some set of cosets. Okay, right, let B sub G be the set of all little b in G such that KB, the coset for B, right, is an element of B. I mean, we want to show that, basically we want to show that BG, BG is, that B is BG mod K. That's what we're getting at here. So BG, it's a set of all elements in G whose coset is in the subgroup B. Remember, B is a set of cosets. Right? It's a set of cosets of K. BG is in G itself. So I'm just calling it BG. Should we call it BG? We could call it B hat or something. Well, anyway. Let's call it B, like above, for the thing above. So B bar or B hat, like hats. Okay, so B hat's the set of all little b in G, such that the coset for little b is in the subgroup B. Okay, so let's show. Well, I'll leave this to you. It's straightforward. It is straightforward to show that B hat is a subgroup, well, to show that K B is a subgroup of B hat is a subgroup of G. It's straightforward to show that. Okay, I mean we've talked about proving such and such as a subgroup plenty of times, so we need not go over that sort of thing again here. So it's straightforward to show that, and simply now by definition, it's got to be that B hat mod K is B, right? So now by definition, of B hat mod K is B. Right, so that function that goes from A to A mod K, right, is surjective because B is, the image of this B hat. Right? Subgroup B is the quotient of B hat mod K. Function is surjective, and then function is one-to-one. Injection. All right, how do we show that something is an injection? So say that B hat mod K is not equal to A hat mod K, right? Or is equal to, I'm sorry. B hat mod K is equal to A hat mod K. Okay, so right, to show a function is surjective, you have to show that if their images are the same, then their pre-images are the same. So say that A hat mod K is equal to B hat mod K, therefore for every X in B hat, right, KX is an element of B hat mod K, which is equal to A hat mod K. So X, which is in B hat, is in A hat. Right. Also, for every X in A hat, right, KX is an element of A hat mod K, which is equal to B hat mod K. So X is an element of B hat as well. Right. So A hat is a sub, or B hat is a subset of A hat, and A hat's a subset of B hat. So they're the same. So A hat equals B hat. Right. We showed that. So this one is B hat is a subgroup of A hat, and this is A hat is a subgroup of B hat. Right. So A hat is equal to B hat. It's subgroup rather than subset because, of course, these things are subgroups, which we showed in the previous part. These things are groups, which we showed in the previous part. So that's it. So that's the correspondence theorem. So, for example, let's take a look at which one should we look at? How about D12, right? It's equal to the symmetries of the regular hexagon. Okay, D12 contains R. So there's 1. R squared, R to the third, R to the fourth, R to the fifth, where R is rotation of 60 degrees, right, for your hexagon. Right, rotating 60 degrees clockwise, say. And then you also have RB, or RB squared, or R squared B. Oops, technical difficulties. Pause. Okay, we're back. So D12, the symmetries of the regular hexagon. So where R is rotation of 60 degrees, 1, 2, 3, 4, 5, 6, and just rotating this way. And B is reflection. We'll say around horizontal line like that. Or 1, 2, 3, 4, 5, 6. So this is the permutation 1 through 2, 3, 4, 5, 6. This is the permutation 1, 2, 3, 6, 4, 5. And a normal subgroup is the following. 1 r to the third. That's going to be a normal subgroup. You can check that. That's a normal subgroup of D12. Okay, so why is that a normal subgroup? Should we check that? Well, we need to check that. I think we need to get the relationship between these two things here. 1, 2, 3. So RB is equal to 1, 2, 3, 4, 5, 6. 1, 2, 3, 6, 4, 5 is equal to well, is there a way to show that more simply? Yeah, if you rotate 180 degrees, right? If you rotate 180 degrees, right, 1, 2, 3, 4, 5, 6, then you get down to 1, 2, 3, 4, 5, 6. Then you get to 1, 2, 3, 4, 5, 6. So that's r to the third. And then if you do b, you get 5, 4, 5, 4, 6, 3, 1, 2, which is the same as if you did b first. Right, 2, 1, 3, 6, 4, 5. That's if you did b first, and then you rotate 180, you get that. Right, 1, 6, 5, 4, 3, 2. 1, 6, 5, 4, 3, 2. Right, so z, this is actually the center. Z, which is 1 r to the third, the center, it's always a normal subgroup. Right, so D12 mod Z has order 12 over 6, which is, or 12 over 2, which is 6. Right, and D12 is not abelian. So D12 mod Z is not cyclic. Remember that one? The center is not abelian, so D12 mod the center can't be cyclic. Right? Because if D12 mod the center is cyclic, then D12 had to be abelian, if you remember that theorem. So D12 mod Z is isomorphic to, well, there's two groups of order 6. There's Z6 and D6. Right? Z6 and D6. Well, it can't be Z6, so it's got to be D6. All right, so the subgroups of the subgroups of D6 are as follows. All right, so you've got D6, and then you have one subgroup of order 3. So D6, let's give these elements a name, 1, x squared, and then y is the reflection, xy, x squared, y. You have one subgroup of order 3. All right. And you've got 3 subgroups of order 2, one for each reflection, which are not contained in there. Let me see, how can I draw this? Yeah, one subgroup of order 3, several subgroups of order 2, 1 y, 1 xy, and 1 x squared y, and then you've got your subgroup of order 1. Right, so the subgroups of D12, which contain the center, correspond to these. All right, so the lattice of subgroups will look exactly like that. Okay, so that's just one more topic in section 8.3, and that's all for the discussion today. And in the lecture, we will start actually on chapter 9 today.